I'm Benny Cutler. I'm a 10th grader at NSU University School, and I'm here to help you guys study for your AP exams, which are coming up in a few weeks. So today I'll be covering units 4 and 5 of AP Calculus AB, which are applications of differentiation. So we'll get started with 4.1. So the first thing that College Board wants you to do is to be able to interpret the meanings of derivatives in context. So in this question, all questions, or at least most questions in this video, are from albert.io, which is a website that has plenty of practice questions, and that's a good resource if you want that. So here it's asking, the population of a small country is modeled by the function p of x, where x represents the number of years since 2000. Which of these is the correct interpretation of p prime of x with the derivative of p of x, including appropriate units? So as a general rule of thumb, whenever we're talking about the units of derivatives, it's always going to be the unit of the original function. So this is talking about population. So if we're talking about population, that's going to be measured in people. So people, excuse my handwriting, p of x is in people. So now, whenever we're taking the rate of change of something, in this case, we're taking the rate of change with respect to time, years. So when we're taking the rate of change, we do per whatever that time unit is. So here, p prime of x will be measured in people per year. So let's see which one of these choices matches up. So p prime of x represents the number of people living in the country x years after 2000. That's what p of x represents, so that's off. P prime of x represents the rate of change of the population x years after 2000, measured in thousands of people. That seems like it's right because it's, except for the fact that the end says measured in thousands of people. But here we have that the derivative is measured in people per year, so we know that that can't be right. And then p prime of x represents the number of people living in the country x years after 2000, measured in people per year. So that seems like it's going to be our answer, but let's check D anyway. P prime of x represents the rate of change of the population x years after 2000, measured in people per year. So let's try to find the difference between these two. They seem very similar. So we have it represents the number of people living in the country, or that it represents the rate of change of the population. So the number of people, that matches up with p of x, not p prime of x. So it looks like D is going to be our answer because it has the rate of change of our population, which is what we're looking for when we're dealing with derivatives. And it's right. Okay. And unit 4 or unit 4.1 is going to ask, for the most part, just what do derivatives mean in context like this problem. And the general rule is you just add a per second, a per year, and make sure that you're talking about the rate of change and not whatever the current population is in this case, or the current value. Okay, 4.2, this is straight line motion. So a lot of the times they'll be talking about a particle moving in a straight line, or say a bug walking on a line. So this will be your number line. Let's say this is your particle, and it's going to be moving back and forth according to this function. This is S of t means the position of the particle. So if we plugged in the position at time t equals 1, so that could be 1 second, 1 year. In this case, it doesn't say, it doesn't matter, it just says at t equals 3. So we don't have to deal with seconds or years. But we know that whenever we plug something into this function, a value of t, we're going to output the position of the particle. So let's say this was -1, and we're talking about time t equals 3 or 4, then S of 4 is going to be -1 because that's the position at that point. But we're also going to be asked for the velocity or the acceleration. So the position or the derivative of the position is equal to the velocity. So that makes sense. If you're moving in a car, your speed or your velocity, that's given by how fast your position is changing. So, and then similarly, the derivative of the velocity, v prime of t, is equal to the acceleration of the particle. So you're going to be tested on these in the AP exam. They're going to want to see if you know the relationship between position, velocity, and acceleration. So it's important to know this relationship here. So let's look at the problem. A particle moves along a straight line. Its position can be modeled by this function. For t is greater than or equal to 0. We're only concerned with t equals 3 here, so we don't have to worry about that. And we're looking for the particle's acceleration at t equals 3. So if you remember what we did in higher order derivatives, we know that acceleration is the derivative of velocity, and velocity is the derivative of position. So we know that acceleration is going to be equal to the second derivative of position. So we know that based on this position function, we can find the acceleration at a point just by taking two derivatives here. So using the power rule, we have 3t squared minus 4t plus 5. And that is v of t. And now we need to take another derivative because we're looking for the acceleration. So now we do with the power rule again, 6t minus 4 equals a of t. And now to find the particle's acceleration at t equals 3, right here, we just plug in 3 to this t right here. So we have 6 times 3 minus 4 is equal to a of 3. So that equals 18 minus 4, which equals 14. And that's one of our answer choices. So if we click on it, it's correct. And that's pretty much straight line motion. It'll ask you what's the velocity or acceleration of a particle at a point based on a function. And sometimes you'll need to find out at what time does the particle change direction, but that's in the next part. So another question is the position of an object moving along a horizontal line, and you want to find the intervals where this is speeding up. So the way to do this, we're going to have to use something called critical points. So critical point, critical point is just going to be any time where the derivative f prime of x, it could be f, it could be g, it doesn't matter, just some function, or f prime of c, because we're not talking about generally. So c is just a replacement for any number. We could choose any point. We're just looking for a place where the derivative at that point is either equal to 0, undefined, yeah, I believe it's just 0 and undefined. So that could be, undefined could just be when it's something over 0. It could, graphically, it could look like an absolute value function. Remember that the derivative right here is still equal to, is still undefined. So that can be considered a critical point. So to find the intervals where something is speeding up, we're gonna have to use these critical points. So to find if the speed is positive or the velocity is positive or negative, so if it's going forwards or backwards, we're going to have to take the derivative of this to find the velocity function. So using the power rule, we have v of t equals t squared minus 6t plus 8. I'll erase this. So we want to find where this, since there's no denominator, it's not a fraction, this can't be undefined, so we're just looking for where this equals 0. So we can factor this as t minus 2 and t minus 4 equals 0. And we know we have zeros at t equals 2 and t equals 4. So now to find, and the next step, now that we have these zeros of the velocity function, we're trying to find out where it's speeding up. So that sounds a lot like acceleration. That's the definition of acceleration, except this is a little different. We're not just looking to see if the acceleration is positive, to see if it's accelerating forwards, because if you're in a car and you're going backwards and you start going backwards more quickly, that would technically be negative acceleration, but the car is still speeding up. You see it going faster, just in the negative direction. So we're gonna have to look for times where the signs of v of t and a of t are the same. So v of t and a of t, same sign. So that could be positive and positive or negative and negative. Because if you're moving forward and your acceleration is positive, you're moving forward more quickly, then you're speeding up. And if you're going backwards, the velocity is negative, and your velocity is getting more and more negative, then you're still speeding up. So to find out what points that they have the same sign, we also have to look at the acceleration function. So the acceleration is just the derivative of this v right here. So we can use the power rule. 2t minus 6 equals 0, which equals 2 times t minus 3. T equals 3 is 0. So let me clean this up a little bit. Still not that clean, but we can work with it. So we know that when something equals 0, it's changing sign at that point for these simple polynomial functions. If you look here, if you plug in, let's say 0, which is less than the 0, 3, we have 2 times 0 minus 3, which is negative 3 times 2, which is negative 6. So we know that when the time is less than 3, the acceleration is going to be negative. So a of t is less than 0 for x, or for t is less than 3. Okay, so that tells us when the acceleration is negative. And then vice versa is true. The acceleration is positive when t is greater than 0. So we're going to look for the times where the velocity sign and the acceleration sign are the same. So if we look here, and the first thing you do is plug in a point to just see if the velocity is negative on that interval or positive. So here, if we plug in 0, which is less than 2, we have 0, we have 0 minus 2, negative 2, times 0 minus 4, negative 2 times negative 4. We have that the acceleration, the velocity is positive. So v of t is positive when t is less than 2. Okay, so if it's positive when it's less than 2, 2 is less than 3. So every time the velocity is positive on this interval, the acceleration is going to be negative. So we know that t is less than 2 is not going to work. You know that t is less than 2 is not going to work for our purposes because we're looking for the times where the acceleration and the velocity have the same sign. So here it's positive and the acceleration is negative, so that doesn't work. So now I'll open a whiteboard. So what was it? We had v of t equals t minus 2 times t minus 4, and then a of t equals 2t minus 3. So we know that t is less than 2 is not going to work because v of t is positive, a of t is negative. So now let's check in between 2 and 3, because that's where the velocity or the acceleration are not going to change at that interval. So we're just looking to see if it works there. So if we plug in, let's say 2.5, we have 2.5 minus 2, which is 0.5 times 2.5 minus 4, which is negative 1.5. Then we have a negative number equals negative. We don't care what that negative number is, we just care that it's negative. So now let's look at our acceleration function. So we have 2 times 2.5 minus 3, which is negative 0.5. Negative 0.5 times 2 is negative. Negative times a positive equals negative. So we know that when t is between 2 and 3, the velocity is negative and the acceleration is negative. So this works. We're going to want to circle this to come back to in our answer. And then now let's check between 3 and 4, because the acceleration changes signs at t equals 3, but the velocity function does not. So let's see what happens here. So if we plug in something like 3.5 to both of these functions, we have, I'll erase this. If we plug in 3.5, we have 3.5 minus 2, 1.5 times 3.5 minus 4, negative 0.5, negative times a positive equals negative something. We don't care what it is. And now if we look at acceleration, we have 2 times 3.5 minus 3. 0.5 times 2 is positive. Positive and negative, that does not work. So when t is between 3 and 4, the velocity is negative and the acceleration is positive. So we know that this does not work. Okay, and our last interval that we can check is when t is greater than 4. So let's try 5. We don't have to do a fraction because we're not doing between 2 points. We don't need to do 2.5 just because or 4.5 just because we're not bounded by another number. So if we plug in 5 minus 2 times 5 minus 4, these are both positive, so that's going to be a positive. And if we plug in 5 to the acceleration, 2 times 5 minus 3, it's going to be positive. So we know that between 4 and infinity, they're both going to be positive. It's positive, and a of t, it's also positive. So that works. So these are our two answers right here. So now let's go back and see if that matches up with any of our answer choices. So between 2 and 3 and 4 and infinity, that looks right. And it is. So that's how you do those. Those take a little bit more work. You don't always have to calculate explicitly what the acceleration is or what the velocity is, as long as you know the sign is positive or negative. So those can be a little time consuming, but just remember, you can always take up less time if you think of it as positive and negative. Okay, so the next topic is a pretty big topic. It's related rates. So this is just talking about derivatives in context in a different way. So to start, we'll look at this question. The volume of a cylinder with radius of 5 inches is increasing at a rate of 36 pi inches cubed per minute. How fast is the height changing when h equals 10 inches? So to start, let's draw this out. Let's go to a whiteboard. We can clear this. So we had 5 inches, 36 pi, and h. So that's a bad cylinder. I'm gonna redraw one. It's a slightly better cylinder. So we know that the volume of the cylinder with a radius of 5, so r equals 5. I don't think you can see this right now. I'm just writing it down so we remember. R equals 5. Height equals 10. Ooh. Oh, and it's all back. Okay, let's try this again. We have a cylinder. The radius of 5, which is constant, 5. And the height is changing at a rate of 36 pi inches per second. So we're going to write this as the derivative of the height. So dh with respect to the time. So how fast is the height changing over time? And they said that that was 36 pi inches cubed per minute. So now we're asked to find how fast is the height changing when h equals 10. And we have to remember that this h right here is not constant. Not constant. And this is constant. We know that r is constant. So before we take any derivatives, we have to remember that r does not change in a cylinder. So we plug that in before we take a derivative. So we have v equals 5 squared, r is 5, and 5 squared is 25. So 25 pi h. Now we can take the derivative. So we have dv dt equals derivative of 25 pi h. We have to remember to use the chain rule. So 25 pi, h goes to 1, but we have to multiply by its derivative, dh dt. So notice that this derivative expression does not include h anywhere. It includes dh dt, but not h. So, and that's because if you think about it, when we're adding volume to this cylinder, its height is changing at a constant rate. It doesn't matter what point on the cylinder you are. The height here is going to be changing at the same rate as the height over here. It's not a cone, so which we'll do later. A cone, the rate of change of the height would be different at different points because it gets narrower and wider as you change the height, but here it's not dependent on height. So now we can plug in our known variables. So we have no dv dt is 36 pi equals 25 pi times dh dt, which is what we're looking for. Now we isolate dh dt. So we have dh dt equals 36 pi over 25 pi. The pi's cancel out. So we get 36 over 25. Now let's see if that matches up with our answer choices. And sure enough, it does. Since we're adding water, the rate of change is positive. So we have 36 over 25, which was our answer. There we go. Okay, now this is a more difficult type of problem called a shadow problem. Just a little bit similar to a cone problem, but we'll do that in a second. So we're told a 6-foot-tall man walks towards a 30-foot-tall streetlight at a rate of 2 feet per second. What is the rate of change for the length of the man's shadow when he is 5 feet from the light? So first thing that we do is we draw this out. So this is our man, this is our shadow. Not the best representation, but we're looking for how fast his length changes. So we can split this triangle up into 2 pieces. These two are similar triangles, which if you remember from geometry, which I doubt you do, we're given that the height of the street pole is 30 inches, I believe. 30-foot tall street light, and the man is 6 feet tall. Make that look more like a 0. And we're looking for 6-foot tall man at a rate of 2 feet per second. And we're looking for when he's 5 feet from the light. So let's call this distance x and this distance y. And these two are both changing with time. So we know that similar triangles, the ratio between the sides has to be the same if they're similar triangles. So 30 over 6, if we have that ratio, 30 over 6, that's a 30, not a 36, equals the ratio of this side on both of the triangles. So if we look the length of this whole side of the big triangle is x plus y, and then we're dividing it by the smaller triangle side, which is just y. And now if we clean this up by getting rid of the fractions, we multiply both sides by 6y. We have 30y equals 6x plus 6y. And then if you notice, we can take this 6y and bring it to the other side. And we have 24y equals 6x. So if we divide both sides by 24, we get y equals 1 over 4x. And this is going to be the same no matter where we are in the shadow problem. This ratio is always going to be the same because they're similar triangles. So now I believe we were given that the rate of change of the distance between the man and the pole, which is x, so dx dt equals 2 feet per second, I think it was. So he's walking this way. And now we can take the derivative of this part. So we have dy dt equals 1 over 4 dx dt. Now, if we look at our given variables, we have dx dt equals 2. So we have dy dt equals 1 over 4 times 2. Or actually, it would be negative 2 because we're walking. No, it would just be 2. 2 times 1/4 is 1/2. So this is the rate of change of this width right here of the shadow. It's not a good drawing, but that's the width of the shadow, and we're looking for how fast it's changing. Now, if we go back to our problem, we'll see that 1/2 is on here twice. Looking if the length of the shadow is decreasing at a rate of 1/2 foot per second or increasing at that rate. So if he's getting closer to the shadow, to the street lamp, the shadow is going to be getting more narrow, because if when I did the problem, the rate of change of x was actually negative, because if we look back to the whiteboard, if we look, x is decreasing. So dx dt is really negative 2, not 2, because you're going to the left, and this distance x is decreasing. So if x is decreasing, then we know that y, because if we plug in negative 2 here instead of 2, then we get negative 1/2. And if a rate of change is negative, that means just something is decreasing at that rate. So now if we go back to this problem, we know that it's decreasing at 1/2 foot per second. Okay, next topic is the last topic of Unit 4, which is linear approximation. So this can come in handy if you don't have a calculator. You're never going to be asked this on a calculator section, I don't think. But this is essentially a way to find an approximate value of a function at a point that you can't really evaluate easily. So here we have cosine squared. We'll read the beginning in a second, but we have cosine squared of 3.5. Now, if we don't have a calculator, we have no way of knowing what cosine squared of 3.5 is. We can make a guess based on pi being 3.14 and 3.5 being a little higher than that. That's not going to give us a very accurate answer. So a better way to do this is linear approximation. So we can use the fact that a derivative approximates a function at a point. So here we have cosine squared of 7x, and we're looking for, so we're finding the linear approximation of this at x equals 0, then using that to find the value of the function at x equals 0.5. So we're trying to find this value around here. We're trying to find this without this graphing calculator. So what we can do, we can take the derivative of this function. So we have to use the chain rule a few times here. We have 2 cosine 7x, because the exponent comes down, times the derivative of cosine 7x. So then we have times negative sine 7x times derivative of 7x, which is 7. So now if we combine this all, we get negative 14 cosine 7x sine 7x. And we're looking, oh, and then derivative of x is just 1, so plus 1. And now we're looking for this at x equals 0. So the way to do this, you essentially find the tangent line, and then you use that tangent line as an approximation of the value at 0.5 in this case, but it'll make more sense once we do a problem. So here if we plug in 0, this is the derivative at 0. We get cosine of 0 is 1, so negative 14 times 1 is negative 14. Then sine of 0 is just 0, so this whole thing just cancels out and we're left with 1. So we get f prime of 0 equals 1. And now to find the slope of a tangent line here, we do y minus y1. So if we go to our function and our original function up here and plug in 0, 0 times 7 is 0, cosine of 0 is 1, 1 squared is just 1, plus x is 0, so we have 1 plus 0, which is 1. So our y value, I'll just write here, f of 0 equals 1. So our y value is 1, so we can do y minus y1, which is 1, equals our derivative, which is the slope of that line. We have here that it's 1, so we'll just leave it 1, and then it's at x equals 0, so x1 is 0, so it's just 1 times x, which is x. Then we get our tangent line as y equals x plus 1. So now to find the value at 0.5, which we know that because 7 times 0.5 is 3.5, and 0.5 times 1 is 0.5. So now we just plug in 0.5 right here, and we get 0.5 plus 1 equals 1.5. And that is our linear approximation to this not so linear function. And now if we look at our actual value, actually let's plot our tangent line to make this easier to see. So this is what we use to approximate. It doesn't look like a very good approximation in this case, but it actually does work out pretty well for us at this point. So at x equals 0.5 right here, y is 1.377. So that's a pretty good approximation considering we didn't have to evaluate any crazy cosines. So our estimated value is up here, but our real value is really somewhere down here. So that's a pretty good estimate considering what we were given. And that's essentially linear approximation. So this won't be this will be a section of an FRQ at most, but it's still good to know in case in other cases in math you ever need to evaluate a cosine function without a calculator, you might want to use some linear approximation. So that's all of Unit 4. So thanks for watching that Unit 4 part. I'll put a timestamp indicating that this is the end of Unit 4. And then now we'll get started with Unit 5. So now we're going to start with Unit 5 of AP Calculus, which is Analytical Applications of Differentiation. And since this is pretty similar to Unit 4, Contextual Applications of Differentiation, I'm grouping these two together because they're pretty similar. So we'll get started with Rolle's theorem and the mean value theorem. So what Rolle's theorem tells us is that if we have this graph here, and the average rate of change between these 2 points is 0. So if we drew a line from there to there, the slope would be 0. Then that means at some point on this curve, the derivative must be 0. And that makes sense because if we look here, this line, the slope of the whole line is 0. If we go up here, if we do anything other than just going in a straight line, we're going to need to go down and then back up, or up and then back down. So either way, at some point, in this case, for this graph, it's this point, the slope is 0 because it's changing direction. And here it's this point because the same reason, it's changing direction. So any curve with these 2 points as endpoints, if it's continuous, must satisfy the condition that there's a point somewhere on this curve in between those 2 points with a slope of 0. And the mean value theorem is essentially just saying the same thing, but generalizing it to anything, so something that's not 0, just a flat line. So here we have a curve with a secant line, which is the average rate of change between these 2 points. So this is the slope of the line between these 2 endpoints. And because the graph comes up and comes back down, at some point, at this point, the point up here with the tangent line, there has to be some point where that has the derivative that's equal to this slope. And that's just because if you go up, you have to come back down to make sure that you get from between these 2 points. So conceptually, that's not too bad. And you'll just have to, when you answer a question, you'll just have to say, oh, if the endpoints have this slope, then there has to be some point between those that has that slope. So that is a derivative. So that's the mean value theorem. The next thing that we can do is find the global and local and global minima and maxima, which is maximum plural or minimum plural. So if we want to find where's the global minimum of this function on the interval, so the first thing we want to do is we want to find everywhere where the derivative is 0, because the places where our derivative is 0 are usually where, if we have a hill like this, then the place where the derivative is 0, is going to be this point where it changes direction. And that is a maximum in this case. So we can use this fact to find candidates for the absolute maximum on an interval. So if we take this function, first thing we want to do is take a derivative and see where does this derivative equal 0. So using the power rule, we get 2x minus 5x plus 2x squared. Sorry, not 2x squared. Nope. Just x squared minus 5x plus 6. Then we set that equal to 0. So now we notice we can factor this as x, not plus x minus 3 and x minus 2 equals 0. So this has zeros at x equals 3 and 2. So we know that those are either maximums or minima. So, or we don't know that for sure, but those are our candidates. So what we can do is we can plug those in to the function and see which one has the higher value or the lower value, because we're determining a global minimum. The global minimum just means it's the bottom of a function. The points around it are higher than it, and that point is lower than any point on the graph, or on this interval, 2 to 5 in this case. So if we plug in 2 to this function, to the function, not the derivative, so we do go here. 2 cubed is 8 times 1/3 is 8 over 3 minus 5 over 2 times 2 squared, which is 4 times 5 over 2, which is 10, minus 10, plus 6 times 2, which is 12, and then plus 4. So if we plug all this in, we get 16 plus 8 over 3, which is 56 over 3, I believe. So this value, we're just going to check it against all of our other candidates. So now we're going to check our other candidate, which is 3. X equals 3. I'll do it up here just to make sure I have room. If we plug in x equals 3, we get 27, or 3 cubed is 27 over 3, so 9. That doesn't look good. I'll just do it down here. 3 cubed, so 9 minus 3 squared is 9 times 5 over 2. It's 45 over 2 plus 6 times 3, which is 18, plus 4. So here we get 31 minus 45 over 2, which is 62 minus 45, 17 over 2. So if we look between these 2 points, this 56 over 3 is bigger than that 17 over 2. Let me just check that to make sure. It's almost 20. Calculators come in handy. 56 over 3. 18. Yeah, it is bigger. But now we know that this is bigger of these 2 candidates, but we also have to consider that this value x equals 5. Oh, sorry, we're looking for the minimum, not the maximum. Oh, oops. We had 56 over 3 and 17 over 2. Sorry, I'm still getting used to Zoom. So we know this one is the smaller value of those 2. So that's going to be our best candidate for the minimum so far. But we also have to consider that the graph, the endpoints of this interval could also be the global maximum or minimum on that interval. So we have to plug those in too. Because if we look at this graph, this is the graph of the function. These are our 2 points. And if we were looking for a maximum, let's say, the points where our derivative equals 0 would be here and here. But neither of those is the maximum on this interval. The maximum is really up here, so which is our endpoint. So we need to make sure to plug in our endpoints as well. So to plug in our endpoint, we'll plug in 5. So 5 times 5 to the third is 125. Doesn't divide by 3. Over 3 minus 25 minus 125 over 2 plus 6 times 5, 30 plus 4. So we have, if we find the common denominator, we get 250 over 6 minus 125 times 3. 375 over 6. So then we get negative 125 over 6 plus 34. And you could calculate this, but actually, no, you do need to calculate it. So 34 times 6, we're just going to use 34 times 6. We're just going to use regular multiplication because we don't get to use a calculator. 424, 204, and then we do 204 minus 125. 79 over 6. 79 over 6. So if we look, that is not smaller than 17 over 2. So we know that this 17 over 2 is our global minimum on that interval. So 17 over 2, that's equal to, let's look at the graph. So our absolute minimum is going to be here at 8.5. 8.5. So 1 over 3x cubed. Global minimum. Oh, sorry. We're not looking for the y value. The question is just asking us what x value this occurs at. So if we remember, this occurred at x equals 3. So x equals 3 is going to be our, because if they just gave us the y values, we'd just be able to pick which one is the smallest. So if we pick x equals 3, that is our global minimum. Hopefully you could follow all that math. But it's just plugging in numbers based on the candidates for when the derivative is equal to 0. So next we're going to look at concavity. Concavity basically just examines how a function curves up or downward. So here, if you notice, it looks kind of like a bowl facing upwards. So that's concave up is what we call it. And that means that the second derivative of this function is positive. And conversely, if we have a bowl that's pointing down, like over here, then it's going to be concave down with a negative second derivative. And down here, this is a big bowl facing upwards. So it's going to be concave up for the majority of this part. So now how do we calculate this? I kind of alluded to it. It's where if we're looking for it on an interval, we find out where the second derivative is equal to 0. So we can see where this concavity changes sign. So we can find out when it's positive and when it's negative. So let's find the intervals of concavity for this curve. We can find it because we have the graph here, but let's do it analytically because we might not always be given the graph. So to compute the second derivative, we can use the power rule. First derivative is 2x cubed minus 3x plus 1 squared times the derivative of x plus 1, which is just 1. So I'm not going to include that, minus 6x. And then if we take another derivative, we have 6x squared minus 6x plus 1 minus 6. And this is our function. So we want to see where this changes direction. Or we want to see where this changes 0 and changes signs. So we can find the intervals of concavity. So when we multiply this out, we get 6x squared minus 6x plus 6 minus 6. So these two cross out, and we're left with, when we take out a factor of 6x, we have 6x times x minus 1 equals 0. So now we're going to look for when this function changes direction, this second derivative function, because that's going to give us an indication of when something is going to be concave, change from concave down to concave up or vice versa. So if we plug in some really low value, we know that our zeros are x equals 0 and 1, because that's what would make this 0. So if we plug in something less than 0, let's say -1, then we have -6 times -2, which is a positive number. It's 12. We don't care that it's 12. We just care that it's positive. So we know that, and it doesn't change direction at any point before that. So we know that from -infinity to when x is in between -infinity and 0, f is concave up because the second derivative is positive. CC up just means concave up. It's an abbreviation. I'm not sure if you can say that on the AP exam. I'd be safe and just write the whole thing out. But for our purposes, this will work. So now if we plug in a number that's in between 0 and 1, we get, let's say 0.5. So 3 times negative 0.5 equals a negative number. So we know that it's that between 0 and 1, f is concave down because the second derivative is negative. It's kind of like what we did for our speeding up and slowing down in unit 4. And now we have one more interval between 1 and infinity. So if we plug in a value, let's say 2, we get 12 times 1 is a positive number. So then between when x is between 1 and infinity, so when x is greater than 1, f is concave up. If we look at the graph, this is true at our point at our point 0. So the function is concave up. It doesn't look like it's concave up, but the whole time it's slowly getting less steep. The derivative is increasing. And then up here it curves up. And then at this point, 0, we said, it starts to get concave down and curve downwards. And then at negative 1, or at the point x equals 1, then it starts to curve back up again. So this is what this analysis can tell us, just when a function is curving up and when it's curving down. Okay, so, forgot to mention, when the second derivative is equal to 0, so when the concavity changes signs, it's important that it changes signs. It can't just equal 0. It has to go from negative to positive or positive to negative. And you know this just by plugging in values based on the zeros. If it's a point of inflection, f double prime of x must change sign. That is the condition for a point of inflection, which is what it's asking us here. And it has to be differentiable, which means it's also continuous. And we know that statement is true. But it could change sign and not necessarily be 0. So we look at a graph that looks like this. This would be an absolute value or piecewise function. Right here, the second derivative changes signs, but the second derivative is not 0 at that point. It's undefined. So that would be an example where it would have to change sign, where it would change sign and still be a point of inflection. We don't necessarily know that it has an extreme value there, because if we look at our example from before, there was a point of inflection around here at x equals 1, but the extreme value wasn't until down here. So the derivative, when the derivative equals 0, the first derivative, then that's a critical point. But a point of inflection is when the second derivative changes sign. So we can cross out 1 and 3 because 1 doesn't have to be true. It could be true, it doesn't have to be true. So based on this, we can determine that it's 2 only. So now this is a question from 5.8, but I thought it fit more with concavity. So given the graph, this is where we determine it graphically. For which of the following intervals is f of x concave up and f prime of x concave down? So first, let's determine when f of x is concave up. So this is the graph of f double prime of x. So we know that something is concave up when the second derivative is positive. So they try to trick you by showing you, oh, here's a nice little bowl where it's concave down and concave up, but it's not asking about f double prime of x, which is what this is. It's asking about f of x and f prime of x. So to find if f of x is concave up, we just look, when is this graph positive? When is it more than 0? So if we look from here to here, it's more than 0. So from A to B, I guess it's also at 0, but it's asking us A to B. That is when, I'll write this down. f of x is concave up from A to B, and it's also positive from D to E over here. So D to E, excuse my handwriting, because that's just when the graph is positive. So now we're looking at, so if the second derivative is, if this is the second derivative, if we have a first derivative function that's concave up, or concave down, it's asking, then the second derivative needs to be decreasing, so getting smaller. So the derivative of f prime, that is decreasing. Oh, so that's going to be whenever this is negative, or whenever this is negative and decreasing. I think let's go to our answer choices. So we know f of x is concave up, which answers half of our question, from A to B and from D to E. That looks like toe, but that is D to E. So we can cross out anything that's not one of those. And now if we sketch our graph of f prime of x, we know that the derivative of the f prime of x is increasing on this interval just because the derivative of that is positive. So it would look something like up until B, and it starts going down, and then it goes back up. So it looks something like that. Not the best, but it's good enough. So if we look at this, it's concave down between this A and B because it's increasing and then it starts decreasing. So it goes from positive to negative at B. It's a point of inflection. So I believe that from A to B, it should be concave down. And yeah, it's just because if we sketch the graph of this, which is what this unit is telling us, we'll get to that in more in depth in a second. Then we can sketch the graph and look and see, oh, look, this is concave down around here because the derivative is positive and then it changes to negative. So that's how you analyze concavity graphically. So now this is an actual sketching a graph problem. So if this is the graph of g of x, what's the graph of g prime of x? So remember that the derivative graphs the slope of a tangent line at any point on this graph. So if we look, it's decreasing, the slope is really, really negative, and then the slope goes to 0 at this point. So I'll draw the graph on top of here. This might not go well, but we can try it. So the slope is getting less negative until here it reaches 0 because here it changes direction. Its derivative is 0. And then it gets positive for a little bit and then goes to 0. Oh, wait. Gets positive for a little bit, then goes to 0 over here. And it gets negative and then back to 0. And then it shoots off to, we suppose, infinity. So let's see which of these graphs looks like that. So two of these look very similar. They both look like this little graph that's stuck around here. But now we have to analyze, is this minimum of the graph on these, is that below or above the x-axis? So if we look back at my beautiful drawing here, it should be something like this. We know that the slope is 0, so the value of the derivative function would be 0 at this point. So if we look, if we want to line this up, it's a little bit harder when the graphs aren't lined up directly. but there should be a maximum a little bit greater than 1, and then it goes to 0 when it's a little bit, or yeah, it goes to, actually, I think part of this graph is wrong. And so then it's positive, goes to 0, then it's negative, goes to 0, and then it goes to infinity. Okay, so this little minimum should actually be below the x-axis, which matches up with this graph. And then the rest of it, you just have to sketch it out based on when is the original function increasing, then this graph that we draw should be positive. And if it's decreasing, it should be negative, meaning below the x-axis. And let's see if we're right. We are right. Okay, so next we have a problem that's basically asking you to see what can we guarantee based on some information. This is similar to what we did in Unit 4 and also determining global extrema. So given that f of x is continuous, there's only one critical point on f of x. So that means the derivative only has 1, 0. So there's only one peak or valley on this graph. Only one critical point. So this is at x equals 2. One of these is x equals 2, something like that. And the derivative is equal to 0, which just means that it's a critical point. And then we know that the second derivative is negative 2. So if we know that it's the second derivative at that point is negative 2, then it has to be concave down. So this is really closer to this is closer to being accurate than the other one. The other one wouldn't make sense because that's concave up. So the second derivative would be positive. So we can't definitively determine anything about what the y value is at that point because we're only given information about the derivatives. So we can eliminate those two. A local minimum. Well, this sketch showed us that it should actually be a maximum, if anything. So, but then we know that this is the only critical point. So this is the only time where it changes direction. So if it doesn't change direction anywhere else, that means these have to keep going down. They can't go up because that would mean it has to change direction. And the function's continuous, so it can't just jump up and suddenly start going up. So we know that is not a local minimum. And we know that this is a global maximum because it's a maximum because it's concave down. And because there's only one critical point, this has to be the global maximum because the graph is going downwards around that. And look, it's correct. We weren't supposed to see that, but I guess I'm working the problem anyway. So this is asking, determine the point on the function. This is optimization. So this is just trying to find the most optimum, the best time where you can either shorten something, make something the smallest, let's say distance in this case, or we can make something the biggest. So in this case, we're determining the point on the function f of x equals the square root of x. So if we remember, that graph looks like this. It is closest to the point 4, 0, which should be somewhere like here. We can pull up the graph of this. We won't get to do this on the exam, but for learning purposes, this is good. So we're basically thinking, if we draw a line at any point on this graph, we draw a line here. When is this line going to be the shortest? So graphically, we can reason, okay, it's probably somewhere around here, but that doesn't really do us much good, somewhere around there. So what we want to do is numerically calculate that. And we can do that by using our distance formula, which says that if we call the distance c, c squared, you know that the distance squared is equal to the final point minus the initial point. So the final point is some x value. So x minus 4 It's what we're looking for. X minus 4 squared plus, oh, and we get the 4 because our final point is on the square root of x. And so the slope, we can do, oh, and then our other one is, so this is just our x value minus our x value from this point. So x, whatever that may be, that's what we're looking for part of, and then minus the y value at that point, plus the subtraction of the y values at both those points squared. So we have plus square root of x minus 0 squared, and that's just going to be x. So if we multiply this out, we get c squared equals x squared minus 8x plus 16, and then plus x. So that's going to look like is c squared equals x squared minus 7x plus 16. So now we can erase this to give us some more room. And now we can find out when the derivative is 0. So that means it has to change from the distance getting smaller to the distance getting bigger. So if we look back at our graph, and this distance keeps getting smaller as we go to the right, then at some point around here, we get the closest we're going to be. That's what we're trying to find, that point. This might not be accurate, but it's somewhere around here. And then it starts getting farther away. So this is like a derivative. This distance goes from getting smaller to then getting bigger. So the derivative goes from negative to positive. So we turn this into a derivative problem. So if we take the derivative of this, we get 2c times dc dt, or no, dc dx equals 2x minus 7. So then we know that dc over dx equals 2x minus 7 over 2c. And then we know that this is 0. What we want to find when dc dx is 0. So we have 2x minus 7 over 2c equals 0. And the distance is not going to be 0, so c, we can't plug in 0 at the bottom as one of our points. So we have to plug in when the numerator here is 0. So that happens when 2x minus 7 equals 0, and that happens at x equals 7 over 2. So if we look at our answer choices, only one of those has that, but let's finish it off. Now we have at x equals 7 over 2, the derivative is 0. So that means that's when it goes from getting closer and closer to farther and farther. And now we plug this back into the original function to find the y value. So f of 7 over 2. And then since this is just the square root of whatever our plugged in value is, then it's just the square root of 7 over 2. And we end up with b. So this is kind of similar to related rates in the way that you go about doing it. You think about what general formula can show the relationship between these two values. And and you can find when you're getting closer and then farther by setting the derivative equal to 0, kind of like related rates. And after optimization, that is unit 5. So now we've finished applications of differentiation. I hope you learned something, and I hope you'll join me for integration. And just let me know if you have any questions about any of this, because sometimes I might have not been understandable. So just let me know. Hope to see you for units 6 and 8, which will be coming up next.